Hi everyone, this is Team Applied Force, and this is our presentation for Lab Report 8. Our team members are Jacobo Nava, Julian Duran, John de Santiago, Samantha Armenta, and Yara Velarde. In this lab, we used carts on a track to study different types of collisions and see how momentum and kinetic energy change before and after they collide. Our main objectives were to investigate how collisions affect momentum and kinetic energy, compare elastic and inelastic collisions, explore how using carts with the same mass versus different masses changes the outcome, and connect our experimental results to the theory of conservation of momentum. First, we want to investigate how collisions affect momentum and kinetic energy, and see the difference between elastic and inelastic collisions. We also want to see how using carts with the same mass versus different masses changes the outcome of the collision, and connect our results to the theory of conservation of momentum. To do this, we measure the momentum and kinetic energy of two carts just before and just after they collide. We perform 4 types of collisions: elastic with the same mass, elastic with different masses, inelastic with the same mass, and inelastic with different masses. For each case, we calculate the total momentum and total kinetic energy, then compute the percent difference between the before and after values. Finally, based on those percent differences, we decide when momentum is conserved and whether kinetic energy is conserved.
For this experiment we used 2 Pasco wireless smart carts, one red and one blue, moving on a low-friction Pasco track so that we could focus mainly on the effects of the collisions and not on friction. Each empty cart had a mass of about 0.25 kilograms. For some runs we kept the carts with the same mass, and for other runs we added extra masses so that one cart had an additional 0.40 kilograms for the different mass trials. We also swapped between magnetic bumpers and rubber bumpers on the carts. The magnetic bumpers were used for more elastic collisions, while the rubber bumpers were used for more inelastic collisions where the carts tended to stick together. All of the motion was recorded using a computer-running Pasco capstone software, which tracked the position and velocity of each cart and then calculated the momentum and kinetic energy for us. This setup allowed us to compare what we expected from conservation laws with what actually happened in our data. Now we'll give a quick overview of our procedure. First, we measured or looked up the mass of each cart, including any extra masses that we added. Then we connected both carts to the capstone software and zeroed the sensors so that all of our measurements started from a clear reference point. After that, we ran 4 different types of collisions: elastic with the same mass, elastic with different masses, inelastic with the same mass, and inelastic with different masses. For each trial, one cart started at rest and we gave the other cart an initial push along the track. Capstone recorded the motion of the carts, and then we placed data cursors on the graphs to select one instant just before the collision and another instant just after the collision, either when the carts bounced apart or when they stuck together. From those points, we read the momentum and the kinetic energy of each cart. We repeated trials as needed until we had clean, consistent graphs. Finally, we added the momentum of both carts to get the total before and after each collision, did the same for the total kinetic energy, and then calculated the percent differences to compare our results.
On this slide we have the main equations we use to analyze our data. First, momentum is defined as mass times velocity, so the momentum of each cart depends on both how heavy it is and how fast it's moving. Next, kinetic energy is equal to 1/2 times the mass times the velocity squared. This tells us how much energy is associated with the motion of each cart. To check how well momentum and kinetic energy were conserved, we used a percent difference formula. In other words, it's the absolute value of after minus before divided by the average of after and before, then multiplied by 100%. Small percent differences mean the quantity is nearly conserved in the collision, while large percent shows that momentum and kinetic energy changed more during the collision. This table shows the values of momentum and kinetic energy before and after each collision. On the left, we have the two masses setups, same weight and different weight. Across the top, we split the data into elastic collision and inelastic collision, and under each one, we list the before and after values of momentum and kinetic energy for the blue cart and the red cart, and then calculated the total. For example, in the same way elastic case, the momentum goes from about 0.05 before the collision to about 0.04 after, and the total kinetic energy stays around 0.01. The same pattern shows in the other elastic case with different masses, where the total momentum is about 0.08 before and to approximately 0.076 after. In the inelastic collision, the total momentum stays close to around 0.06 before and about 0.058 after in the same weight case, and 0.09 before and 0.087 after in the different weight case, but the total kinetic energy drops more noticeably. That's why we say momentum is approximately conserved in all these collisions, while kinetic energy is only well conserved in the elastic ones. Table 2 shows the percent differences between the after and before values of the total momentum and total kinetic energy. For the elastic collision with the same weight, we got about 4.8% difference in momentum and 2.02% in kinetic energy. For the different weight elastic case, the momentum difference was about 5.12% and the kinetic energy difference was about 3.38%. In the inelastic collision, the percent difference in momentum stayed small, around 3.39% for both the same weight and different weight cases. But the kinetic energy percent differences were much larger, about 28.57% for the same weight case and 22.57% for the different weight case. So this table supports the idea that momentum is approximately conserved in all four cases, while kinetic energy is well conserved in the elastic collision, but not so much in the inelastic collision.
Hi, my name is Samantha Armenta and I will be presenting graph and lab video and conclusion. For laughing graph video, two smart carts collide on a low friction track in 4 different ways, elastic and inelastic collisions, each with the same masses and different masses. One cart is pushed while the other starts at rest. In the elastic trials, the carts bounce apart using magnetic bumpers, and in the inelastic trials, they stick together using rubber or Velcro bumpers. When the masses are different, the lighter cart reacts more strongly after the collision. Throughout the video, capstone records the momentum and kinetic energy of each cart so we can compare the values right before and right after impact. These collisions visually show that momentum stays nearly the same in every trial, while kinetic energy is only conserved in the elastic collisions. For conclusion, in all 4 cases, total momentum before and after the collision was close but not identical. Small percent differences suggest momentum is conserved within experimental error. For elastic collision, total kinetic energy changed very little, so Ki is approximately conserved. For inelastic collision, total Ki after the collision was clearly smaller, so Ki is not conserved and is transformed into sound, heat, and small deformations. Changing from the same mass to different masses mainly changed the final motions, but momentum was still conserved and only elastic collision conserved Ki. Main error sources: track friction, cart misalignment, cursor timing on the graphs, and sensor calibration. We also have the credits for whoever did what, and thank you.